Hello, friends. I'm Dr. Urmila Joshi, and today we are going to see the second part of cyclohexane conformations. I hope you have understood and appreciated the first part. If you like this video, please hit the like button and subscribe. So, let us go to cyclohexane, the second part. Okay, so in case you have any difficulty, please make sure that you communicate the same on this mail ID that I have given. Okay, so let us begin. Uh, Last time we had seen what is flipping. So first, let us exercise uh, the flip structure writing. So the question is here, write the flip structures of the following. Now for writing flip structures, please try to understand the procedure. Okay, this is a chair conformation. First step is write the flip chair conformation. So the sort of mirror image, but not mirror image of the entire molecule. It is the flip chair. Okay, so when you draw the flip chair, let me use the pointer. This carbon is the lower plane carbon. So now it goes to upper plane. The bond that is pointing upwards remains pointing upwards, but equatorial becomes axial. So now let us try to write. This carbon now becomes this carbon. The bond, just a moment, the bond that is pointing upwards remains pointing upwards, but equatorial bond becomes axial. And so this is the flip structure. Okay, let us go to the second molecule. Okay, this is the second molecule. Now just try to understand this carbon, which we are talking about, is the upper plane carbon. And so the bond that is pointing downwards is equatorial bond. Okay. Now, while writing a flip structure, what you will do is write a flipped ring first. Okay. Then fix the carbon. It will be this carbon, right? This is going to be the carbon. Now, the bond which is pointing downwards remains pointing downwards, but this is an equatorial bond. Just see, part of the tripod-like structure. So, this is an equatorial bond which will now become axial, but pointing downwards will, sorry, let me draw it properly. Pointing downwards will remain pointing downwards. Okay? Everybody follows this. I hope everybody understands this. It is necessary that you are able to write this flip structure. Okay. Let me write the third flip structure. Okay. The procedure again is the same. First, write the flip form of the chair. This is important because once you do this, this will be useful in cyclohexane part. Okay. Upper plane carbon now goes to lower plane. Second point is fix the carbon. This is upper plane. So it goes to lower plane. Bond that is pointing downwards remains pointing downwards. But this is an equatorial bond which now becomes an axial bond. Okay. Over here. First thing, draw the ring in a flip form. Okay. Then fix the carbon. This is the lower plane carbon. Now it goes to upper plane, right? And bond which is pointing downwards remains pointing downwards, but this is axial. This now becomes equatorial. Correct? it is extremely necessary that you understand this flip structure. Now here, okay, draw the flipped ring. First, draw the flipped ring. After you draw the flipped ring, what you will do? You will fix the carbon to which substituent is attached. It is this carbon. This is the extreme left carbon, right to it. This is the extreme left carbon, right to it. Okay. Upper side of the paper, upper side of the paper. It is easier with this denotation. Okay. Now this is pointing upwards. So draw a bond that is pointing upwards. This is equatorial, that becomes axial now. Okay. The last one, I'm again, first step, draw a flipped ring. Now, fixing both carbons is easy over here, two extreme carbons. Now here, lower plane, which has gone to upper plane now, pointing upwards. Upper plane pointing upwards is an axial bond, right? Upper plane pointing downwards. So upper plane has gone to lower plane, pointing downwards will remain pointing downwards. So equatorial becomes axial. Okay, I hope you have understood this. Now let us go to monosubstituted cyclohexane, 1-methyl cyclohexane. Again, I have not written a complete flipped structure. First, I drew the flipped ring. This is the right-handmost upper plane carbon. So now it will become right-handmost lower plane carbon. So it is going to be this carbon. Then this bond is pointing upwards. It will remain pointing upwards. And so axial becomes equatorial. Okay. So this is an axial structure. Methyl group is in axial form. Here the methyl group is in equatorial form. Now, let us try to understand whether energy of both these structures is same or it is different. I have drawn an axial substituent like this in a different type of representation. We have studied this Newman representation earlier. And I have drawn the equatorial structure also in the Newman representation. And here is 1-methyl cyclohexane in axial form. This is a Newman representation. This is a normal representation. Now let us try to understand whether energies are same or energies are different. Look at this structure. This methyl group is in axial position, upper plane carbon axial. Now when in this format, it faces 1,3 diaxial interactions from these two hydrogens. Okay, these are also upper plane axial hydrogens. So all of them are in the same plane and they face 1,3 diaxial interactions, which increase the energy of the system. Okay. Now, second interaction is a gauche interaction. Now, let us try to understand what is a gauche interaction. I think we had seen this in case of butane, the gauche interaction. I'm writing it over here, the butane structure. Okay. This is CH3 and this is another CH3. So this is a gauche structure. These two carbons are nearby each other and face some repulsions. Similarly, look at this structure. This methyl group and this CH2. Are they exactly in the same position like the gauche interactions? Yes. Look at this. this methyl group and this methyl group. The interactions are same. So they face a gauche interaction also in addition to 1,3-diaxial interaction. Now, how many gauche interactions? Look at this figure and you will understand. The gauche interaction is between this carbon substituent and the adjacent carbon substituent. So look at this carbon substituent. There are adjacent two carbons. I hope everybody is able to follow this. This is the carbon to which methyl is attached. There are adjacent two carbons. And because there are adjacent two carbons, there are two gauche interactions which cyclohexane faces. Now the 1,3-diaxial interactions as well as the gauche interactions make this molecule, just a minute, make this conformation, the axial conformation corresponding to more energy. In other words, 1-methyl cyclohexane is more stable in equatorial conformation where it has no 1,3-diaxial interactions and no gauche interactions. And so the energy of the conformation when methyl group is in equatorial form is less. Now look at the distribution of the axial and equatorial conformations. If the substituent, if this is cyclohexane and the substituent, say R is F, then F has a smaller size and so 40% can remain in axial, 60% in equatorial. Still the preferred conformation is equatorial. In case of methyl group, 5% axial, 95% equatorial, because methyl group has a larger size, and because of the larger size of the methyl group, the diaxial interactions correspond to a more energy. Isopropyl group, still larger size. So energy of 1,3-diaxial interactions increases further, and so percent axial goes down. Tertiary butyl, huge group. So it is so much near the other two axial hydrogens that the energy of 1,3-diaxial interactions is very, very large, and practically everything exists in equatorial form. Now here, one thing I want to mention, questions have been asked about this cyclohexanol preferring the axial conformation, and the answer that has been given for this has been hydrogen bonding. But let me clarify some things. Suppose this is OH, okay, and this is H. The reason that is given is hydrogen bonding with 1,3-diaxial hydrogens. But when I confirmed it in the latest books, it is given that this also remains, cyclohexanol also remains in equatorial form. But if there is a question why it remains in axial form, you can mention that there is hydrogen bonding. Hydrogen bonding is not possible because this hydrogen is not attached to a heteroatom, and so hydrogen bonding seems difficult. Now coming to disubstituted cyclohexane. First, 1,1 disubstituted cyclohexane. I have drawn the structure over here. Now this one dimethyl cyclohexane. But when we come to 1-methyl, 1-tertiary butyl cyclohexane, will there be two different energetic conformations or both conformations will be same? Just have a look at conformation number 1 and conformation number 2. Okay. Conformation number 1 has methyl group in axial position and tertiary butyl in equatorial. Conformation number 2 is a structure where tertiary butyl is in axial position and methyl is in equatorial. Now, which one will correspond to higher energy? Obviously, conformation 2 is going to correspond to higher energy because the huge tertiary butyl group is facing 1,3 diaxial interactions from hydrogen. And so this will be corresponding to higher energy. This will be corresponding to lower energy. Is that clear to everybody? Now, coming to geometric isomerism in disubstituted cyclohexanes. Okay. This is when both the substituents are in different places. Okay. So, I'm writing this. Here is a structure 1,4 disubstituted. Okay. This is the structure. Another structure can be this and this. Now here both are pointing upwards. Okay. One axial, one equatorial is all right. Both are pointing upwards. So this is a cis isomer. Here one is pointing upwards, one is pointing downwards. So both are trans isomers. Okay. With this, we are ending today's lecture, and the last lecture will be about stability of geometric isomers and optical activity of disubstituted cyclohexanes. Okay. With this, we are ending today's lecture. And there are some examples over here. Identify whether the following structures are cis or trans. You can have a look at this video and then identify whether the structures are cis or trans. Okay. Now, I am stopping at this point. In case there is any difficulty, please feel free to contact me on the mail ID. Thank you.